Okay, so if I'm holding the molecules like this, what type of substance would they probably be?
Gas.
A gas, good, yep. And then liquids, they're touching as a liquid, right? But they're just like, can move. But then a solid, stuck in place.
I heard this weird thing where there's like a 1 in like quadrillion chance or something where if you like slap a table that your hand will go through. Is that like actually true?
I've never heard it.
Like almost like.
But based on their forces, right? If it happened to be a time where they like weren't linked up, I guess so.
Yeah, I heard something like that.
I don't know. I've never heard that, but it seems fun. Seems like a cool idea. Everyone, let's try it. All period, right? How many times? We do it every day, all year long. So I don't know. I'll have to look into that though. It seems, once again, it seems weird, plausible, but definitely in a weird way. So, okay. So as we talk about these properties, that's the thing to remember, right? Is remembering to visualize at the molecular level. That's what helps this make so much sense and takes away like just trying to memorize like, oh, this is high, so this must be low. Like, don't memorize them, just think about it, and it really does like make sense. And that's the hope with the demonstrations we're gonna do today, that's what we'll see. So the first one I've already done for you on your demo paper. I'll still let you see it, but I wanted to write an example of wording to once again help us in our FRQ justifications get to where they need to be. Okay, so I'll pass these around so you can try it too. These are called hand boilers. So you kind of know what's going to happen. But they have a substance in there. If we were doing this and you didn't know what the answer was, your job would be, what claims can you make about this blue liquid based on what you observe? So what happens is if you hold these things from the bottom, and there you go, you can actually, literally, we're causing the liquid to boil inside of it. Now, these are somewhat temperamental depending on the temperature of your hands. So if you're a cold-handed person, it may not work for you. But that's what's happening. So if something boils very easily, that's the observation I just had, what claim can you make about its IMFs?
What's a covalent bond?
That it's probably, we're getting more generic, that it's probably pretty weak, right? If something boils very easily, then its IMFs must be very weak because it's not being held together very much in the first place.
Well, having more than liquid inside, would the liquid be hot or just bubble?
Great question, Izzy. So today you need to separate, like from here on out, your idea that boiling means hot, because it doesn't. From a scientific standpoint, boiling has nothing to do with how hot something is. To us, we're used to it because water's hot when it boils, right? But boiling just means what? The transition of a liquid to a gas. And it doesn't have to be hot to do that. For example, if you put your hand in a container of boiling nitrogen, it would freeze your hand. Because nitrogen boils at negative 300 something degrees, right? So it has nothing to do with hot or cold, but I'm glad you bring that up because it's something you often come in with, like a conceived idea, but you got to separate it from what really is. So, okay, so notice everyone read along, follow along as I read this. So this is how I would write my claim. I said the liquid has weak intermolecular forces. Something with FRQ some of you need to work on is when you are making a claim, put that first. Some of you on Unit 2, I was like having to search your paragraph to be like, what is your claim and all that you're saying? Like, make it very clear, this is what I'm claiming, okay? Then it says, since the substance boiled at a low temperature, so there's the evidence, right? I viewed that. It shows that the molecules are held together weakly, meaning weak intermolecular forces. And then always bring it back to the claim. That once again just makes it very clear to a reader of like, this is what I'm saying, this is why, and it matches the claim I stated, okay? All right, questions on what you're gonna do as we view more demos? Okay, I'll pass these around. Do be careful, they are glass. But I have 4 different ones. They're just different colors for fun. But they're all the same substance. It's a type of alcohol that's inside of it. I think it's ethyl alcohol, which has a very, very low boiling point. So I'll pass those around if you want to kind of see it for yourself. Yeah,
If
Xander.
it has such a low boiling point, wouldn't that mean most of the, or any of the elements not much of a difference in their electronegativity?
It could, or it just means it's perfectly symmetrical, right? And so, but that definitely could be part of it too. Okay, I'll start on back here with you, Devin, and then just kind of zigzag them throughout so everyone can get a chance to try it too, because they're kind of fun. Okay, while we're passing those around, let's take a few notes and then I'll do the next demo. Okay, so one property we see, once again, there's more properties than what we'll talk about, but hopefully after a few of them you'll start recognizing the patterns of how IMFs influence things, okay? So one particular property is surface tension. Okay, so surface tension, once again, this is the fancy definition. It's kind of confusing, but it's all about, right, that at the surface of a liquid, that interaction of molecule to molecule, right, is the surface tension. Okay, so let's build our link first, and then we can talk about some more examples. So I just am going to keep a list over here if you want to put it like, you put it throughout your notes, or if you want to, this is kind of a summary of all the different things we're talking about and how they link to IMFs. So if a substance is shown to have a high surface tension, what connection would that have to IMFs? If something has a high surface tension, what can you claim about its IMFs? Would they be strong or weak, Michael?
Be stronger.
Why?
Because it would take more energy to break through the surface.
Perfect, yeah, because if they're holding, this is how tight they're held together. So if they hold tightly together, then they're going to have a high surface tension. Also why belly flopping into a swimming pool doesn't feel very good. Because literally that's what you're experiencing when you belly flop, is the surface tension of the water, right? That's why, has anyone ever gone up to Park City and watched the ski jumpers go into the swimming pool? It's really cool if you've never gone before. I don't know if they do it all year long or just in the summer, but anyways. For those that have gone, what do they do to the swimming pool?
Put little bubbles in it.
Yeah, so for those that haven't gone, visualize it with me. They have a giant swimming pool. They have ski jumps.
Get Chase Bradley to check out.
Yep. Oh, I don't even know where you are now. I went to a normal seat. She's over here. So they go off the ski jump. They have a life jacket on. They like do a trick, and then they land in the swimming pool. But in order to protect them in case they like don't do it right or they land weird, they break the surface tension with bubbles, and so it doesn't hurt. It's a very similar idea to like using a foam pit for a gymnast, where a foam pit allows them to do a trick and land without getting as hurt as it would if you like tried it on a flat swimming pool. So that's our connection here. It's the higher the surface tension, the higher the IMF would be. Okay? Okay, keep passing the hand boilers around, but everyone look up here for a moment. I'm going to show you the next demo. Okay? So once again, your job, and you have your table buddy to talk to, okay, so you can talk to each other about your ideas, is come up with a claim based on what you observe of the substance's IMFs. Okay? All right, now I am going to tell you what this substance is. Well, you're going to see what it is because I'm about to fill it up. But make sure your answer is based on what you observe, not just the fact that you know what it is. Okay? All right, so I'm going to use water. Okay, so I have a little jar I'm going to fill up with some water here. Okay, well, that was more water than I wanted. Okay, that's not there. Okay, what I have here now is they're just like a laminated card. It's like a piece of paper, but laminated. Okay, I'm going to put that over. Oh, that one's too small. Let's try it. I'm going to put it over the top of it. Oh, why did I use last paper? That one was the perfect size. Yep. Sorry. Let me just search through the cards for the right size one here. Oh, that one looks fine. Okay. So I'm going to take the card and I'm going to put it over the lid so it covers it completely. Okay, everyone observing here. I'm going to flip it upside down. Okay. And then pull the card away. Okay. Yes. All right, so come up with your table buddy. Based on what you observed, what can you claim about the IMFs of the substance? Ready, set, go. We can break up our threesome now since Brandon just lost it.
Hey, did you
Austin, I'm gonna is that okay? Do you want to come join Brandon and be his buddy?
Hush. Did you get the?
Sorry, was that globe in your way for those on that side? You see it okay? Okay, so what did you observe? And then come up with a claim based on what you observed. And I'm sorry, but magic is not a valid claim.
It is October.
It is true, actually.
What about Mickey Mouse?
Mickey Mouse. Yeah, just kidding. You thought you signed up for chemistry, but you're actually at Hogwarts. Yeah, just so I can reuse it.
Typically you do that with any substance?
Yes.
With any, like,
Any paper, yes.
oh, just paper?
But not any
But the substance in
I meant
it.
like cardboard flat.
Oh, yeah, like cardboard, wood, anything flat would do that part
So
for us,
does the
yes.
surface tension just kind of cling to the sides? Like, I'm confused how it like stays like that.
Come up with a claim. There's a variety, like, there's kind of one big answer, but there's a few different ways in which it can be written, so. Did anyone not get to try the hand boiler that wants to hold it? Yes, if it goes, once it goes up.
Why is that? Because it boils hot, but if you switch hands, it's because it cools
So-
off at the bottom, so it goes.
It's just trying to get away from the heat.
Yeah, it's just like the heat's forcing it to like move. Did it not? Some people though, I'm sorry if it didn't work for you. Every once in a while there's a person who's like, oh, your hands are too cold. Alright, I'll give you 30 more seconds to finish up your answer. And then we'll hear a few of them. Okay, if I raise a hand, anyone willing to read their answers so we can hear some different viewpoints? It's your turn.
Observations too.
No, just your like claim evidence reasoning.
So the liquid has strong IMFs because the liquid stays strong in the jar upside down. The IMFs are strong enough to hold itself in with surface tension.
Love it. Yeah, and he stated his claim very clear. It has strong. This is what we saw, and so this must be true. Very good. That's my face fat. Someone else willing to read theirs just to hear maybe the same thing but just in different wording? Let's hear it, Dutch.
I said the liquid has strong intermolecular forces because the liquid did not fall out of the container, showing high surface tension as a result of strong intermolecular forces.
Yeah, it's a mouthful.
Yeah.
Awesome. Love it. Very good. How's my face back? All right, if you said something along the lines that the intermolecular forces must be strong, you can have a smiley face as well. Then Dodge and Tyler, you guys get 2 for sharing this one. Oh, I do. Thank you, Ethan. I think I have yours. Someone else's too. Andrew, I have yours. Oh, how fun. You're right by each other. How convenient. Yeah. Okay, so let's talk a bit more and then we'll do another demo. Oh, I don't want to lie to you, so I do need to be honest. There was kind of a trick to this. If you try it at home, it won't work. I did something to my jar. Now, it is still about strong surface tension, but water surface tension is not strong enough to do what you saw it do. Front-ish row may have seen there's something going on. I try to be like a magician with a stealth in hand. But I have glued onto my jar a window screen. So there are holes, because once again, the water, you saw the water go in and out, but there are extra things for it to grab onto, right, that allow it to stay. Now the interesting experiment I haven't yet tried, but I always wondered is, at what point would weight and gravity overcome the forces? You know, like, could I do an entire bucket of this and like hold it over Jack's head and it wouldn't like spill on him? But or would it be too heavy at that point? You know that the IMFs wouldn't matter anymore. So. I don't have a bucket.
I honestly think it depends on like the surface area of like the opening. So like maybe that surface area wouldn't work for heavier weight, but if it was like wider, like a bucket.
That's what I'm wondering. Yeah, like is there a point?
I wonder if it's like
Like if I didn't put too much in the bucket, right? Like not tons of water, but if it was really.
that it can handle.
But is there a point at which it like? Yeah, I don't know. Maybe I'll have to glue a window screen to this bucket over here.
I think maybe not a bucket because the hole's too big, but you like maybe like a giant like like alcohol jar, just like the one that has like a bottle in it and it goes like this.
Oh
'Cause
yeah.
a bucket, I feel like it'd just be too easy for it to go.
Just come right out.
But
Yeah.
like a bottle, like
A little bit narrower.
Is that why bottles always do like that thing where it falls out really slow just because it, or no, that's just the shape of the bottle.
No,
Well, but it's kind of related to it is like it's the airflow. Yeah. Yeah, because it seals itself, right, as it's coming off. So it's kind of related to it in some ways. So
what are like liquids that don't have strong surface tension? If you did that, would it just like fall out immediately, or would it do like the bubble thing?
I don't know. Theoretically, it would not stay as well, but I don't. There's a range of what that could look like. So I don't know. I've never tested it with anything but water. I don't know. I'll have to think about that, I guess. Okay, our next property is something known as vapor pressure. Okay, now first off, you got to understand what vapor pressure means, because if you don't even have a definition, it's hard to justify it, right? So the word vapor is used to describe a substance that that exists as a liquid, but is turned into a gas. So like, for example, it's actually pretty rare for us to call water like water gas. We call it water vapor, because water naturally is a liquid. Versus something that is just naturally a gas, you just call it a gas. But a vapor is just a different word for something in a gas phase, okay? So what vapor pressure is, and we'll talk tons about pressure next week, because next week is learning all about gases and their properties and things like that. But the basic idea of pressure is visualize a container with bouncy balls in it, okay? Pressure is a measure of how hard and how often the bouncy balls are hitting the sides. So the more they hit and the harder they hit, the higher the pressure is going to be, okay? So now keep in mind, to have vapor pressure, you have to have a closed system, okay? Label that lid to emphasize that. Like, it has to be closed, because if it's not closed, where's the vapor going to go? It's just going to float away, and then you don't get a pressure, right? So in a closed system, the vapor pressure is describing in this space above the liquid how much pressure is going on in there, right? Yeah, Izzy.
Would it be possible, say, if you fill one of those containers like to the brim with water, and there wasn't any like air in it, and you started boiling it, would you break the container because of the pressure?
That's called a bomb. A water bomb, I guess. But yeah, I mean, a bomb is literally just, it's stuck in a container and it wants to get out. And so, yep.
So, why do we call it water vapor? Because we came up with ice and water.
Why doesn't it have its own special name?
Yeah.
I don't know, that's a good question, Robbie. What would you call it? That's a good question, I don't know. Maybe just because we don't like use it, like we use ice, you
It's
know?
called steam.
I think we should just start calling it solid water. Try some solid water with nice air. That's what we should just do. So, okay, what's our connection? If something has a high vapor pressure, what is the connection to IMFs? Is it high or low? Show me with your finger what you think. Take a guess. If something has high vapor pressure, so there's lots of bouncy balls. There's lots of bouncy balls up here. Paxton, why is it low?
Because it evaporates easier, so the IMFs are weaker.
Yeah, if it's turned into a gas, that means it doesn't really want to be a liquid. Nothing's holding it in that phase. So this one is oppositely related, right? So water doesn't have an extremely high vapor pressure, but like most alcohols have a pretty high vapor pressure because a lot of those have pretty weak intermolecular forces. So keep in mind the word alcohol in chemistry is like a huge group of things. There's a lot of chemicals that are classified as an alcohol. So, okay, questions on what vapor pressure is? Okay, let's talk again. We kind of already mentioned it, but let's get it down on paper for boiling point. Okay, so boiling point once again is not about how hot or cold something is. It's just the point at which it has enough energy to go from a liquid to a gas. Okay? Yeah, Robbie. Oh, that's fun. Boiling point of a liquid is the temperature at which its vapor pressure equals the external pressure. All right, what would be our IMF connection? If something has a high IMF, what does that mean about its IMFs? Did I just say IMF twice?
Yes.
Rewind. If something has a high boiling point, what does that mean about its IMFs? Point with your finger. If it takes a lot of energy to boil it, that must mean it's held together very tight. That's why, once again, that's why nitrogen has a boiling point of -300. Is it hard to get them to go apart? No, it literally just will go apart on its own.
What's helium's boiling point?
Ooh, like 2 Kelvin? Something like that? It's like, yeah, it's pretty small. So, okay, now a cool thing, well, it's cool in data, it's kind of a really boring lab. So that's why we're not doing it. I actually had to do it in college, so maybe I should have made you do it too. But if you do an experiment where you take solid water, ice, and you put a temperature in, a thermometer in it, and you measure the temperature continuously as you heat it. Okay, so imagine we have like our Bunsen burner. Okay, you have a beaker here, you have your ice cubes. Sotheby's was a really good artist. Okay, and then you're measuring it with a thermometer. Okay, and then we're heating it up. What's really interesting is the data you get through this phase change process. So as I'm heating the ice, we see the temperature go up and up and up and up. But then the temperature stops changing. But I haven't turned off the stove. But the temperature stays constant during a phase change. Any thoughts of why? Why would it not actually get hotter while it's phase changing, Ethan?
The rest of the water needs to absorb all the heat before it can get hotter.
Yeah, all the energy is being used to break the intermolecular forces. Because remember, definition of temperature in chemistry is what? Just movement. So if it's getting hotter, it's because these are moving faster. Well, during a phase change, all the energy is being used to just pull them apart. But then once they're all apart, then they can start moving faster and faster and faster. Until you really need to pull them apart into a gas. So it is impossible to get boiling water to be hotter than 100 degrees at sea level. We'll talk more about that next time. But like literally you can't get it hotter. Like while water is boiling, it doesn't get any hotter. It just stays at 100. And then what does get hotter is the steam. Right? The steam can get hotter once it transitions, but you can't get water hotter than what it boils at. So, questions on that? As you're kind of changing maybe your view of how to view what boiling is, right? Different from just thinking of cooking mac and cheese, right? Think of boiling a little bit different.
Doesn't cooking like apply to this? Because if you're at like a different, if you're not at sea level, doesn't the temperature for kind of change
Yes.
for what you're
So we'll talk
cooking?
more about this next time, but like for example here in Utah, our water boils at about 98 degrees, and we can't get above it. And if you're like on top of Mount Everest, water boils at like 78 degrees.
Why is that pressure?
That's what it's related to, yeah. So when we talk about gases, we'll talk more about that understanding. Izzy?
So technically would helium not have a boiling point because it never goes into, so like, because we can't put it in a solid, so it would have a boiling point?
As of right now, yeah, we don't know of one because they've never been able to make it a solid.
Melting point?
Yeah, a melting point. Yeah. Tyler?
Does that mean in space water boils at a very low temperature, not like super low, but like
It boils instantly.
instantly?
Yep. So next time when we talk about gases, I have a vacuum chamber, and you can boil water in a vacuum chamber, but it's at room temperature.
Oh, is that why they say when like you're in astronaut space, you get exposed to space, your blood boils?
Yeah, that's why you wear a spacesuit. I mean, variety of reasons, but yeah, because literally your insides would boil. Which sounds nice. Michael.
So if you boiled some things under the sea, would it take a higher temperature?
Ooh, Michael, I've never thought of that.
Well,
I mean, it'd be hard to do.
Yeah.
So theoretically, yes. You could, I mean, I guess here's kind of the answer. That's exactly how, like, do you guys, any of your moms or families have Instapots?
Yes.
Yeah.
Like a pressure cooker?
Yeah.
That's like literally what it's doing, right? Is you're actually, and the reason why they cook so fast is they are able to get water above 100 degrees. And that's why when you release the thing, the steam that comes out is like crazy dangerous because it's super, 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 super hot. But yeah, it's the basic idea of cooking under the sea. That's what you should call it when you use your Instapot next time. Teach your mom that. Or your dad. Either one can use the Instapot. Okay, so this is an example of an AP type question in relation to the application side. So you might see questions on the AP test that are just like our quiz today where it's like, oh, what forces do these things have? But more often the questions look like this. But really, it's the same thing if you just understand what it's asking. So this question says, list the following substances in order of increasing boiling point. So the first thing you need to do is when you read a question that is about a phase change property, your brain needs to say IMFs. This is all about IMFs because IMFs are all about phase changes. So what was our connection between boiling point and IMF? So literally, if I'm putting it in increasing order of boiling point, I'm just putting it in increasing order of IMFs. But if you don't recognize that link, you can get very stuck on these questions with like, I have no idea. But if you all of a sudden just think, oh, I just have to sort them by IMFs, it really simplifies what we're doing. So let's do that and sort them first. So BaCl2, what type of forces does it have? Yep, so this one's ionic, metal with non-metal. All right, H2, what one does this one have? It's just a covalent bond, so then what forces? Yep, just London, because it's not polar, right? Okay, CO. Good, so it is polar, so it got London and dipole. HF. This one's going to have, London, dipole, and hydrogen bonding. So this is where, once again, if you're not strong with like labeling, we've got to get there, right? You've got to be able to look at something and say what it has. Okay, and then finally, NE would just be London, yep. Because once again, it's not bonded to anything, but what we're talking about is an NE in relation, right, to another NE, right? What type of force do they feel? So once you have them laid out, it gets fairly clear for the most part which one is going to have the highest boiling point. Ooh, careful. Yeah, ionic stronger, because keep in mind this is breaking the real bond when that's just breaking the friendship. Okay, so I'm going to put BaCl as my highest. But then what would come next? Yeah, so hydrogen bonding. I'm going backwards just because it felt easier to identify that way. What would come next? Yeah, the dipole force. So now we have the debate of two things, both London. How do I sort them out, Xander?
would neon be stronger just because it's more negative?
Ooh, it is neon, but that's not the Y. But nice try. It's gonna have harsh.
Feels like higher polarizability because
Yeah, there's our fancy word. So what makes it have a higher polarizability?
more electrons.
More electrons. So when you're battling out London, who has a higher London is about who has more polarizability, aka who has more electrons. Because the more electrons allows that greater momentary shift than the other. So, questions on how to do a problem like this? So this is what homework 3.1 is going to kind of have you do. It's going to give you properties, and based on the properties, connect it to the IMF. So, okay. All right, I'm going to do, everybody stand up really quick. Some of you look like you could stretch breathe. And then we'll do another demo. Okay. Now you don't have to do this if you, I don't know, if it makes you nervous. I promise you'll be fine. But if you want to participate, hold both your hands out like this. And I'm going to spray them each with a different substance and just, these are your observations. Okay? But if you don't want to do it, then you can ask someone else what they experienced. That's okay. You don't mind the drips, it's fine. That's why I said try to hold it out back. Did I get them both? Yeah. The look on some of your faces when I spray is quite funny, actually.
The left one feels cold.
It's rubbing off.
Really good.
And it's dry.
Whoa, it's
It's dry. Yeah, it's dry. This is dripping down my arm like normal water.
Yeah, now my bracelets are wet.
I guess I should have to go like this.
On the wash. So dry.
Okay, oh, he's getting sorry about that. Okay, so this is number 3 demo. Okay, so I won't tell you what they are now. I will after. But what claims can you make about the yellow substance or the pink substance?
Which one was on? Which?
You do both?
Ooh, that's a good question. Did I switch hands?
I think pink was left.
Which one?
Spray some.
Okay, this is how I was holding it, right?
Spray some again. Just spray it again.
Does it feel the same?
Yellow's left, pink is right.
Am I okay to wipe the pink stuff on my shirt?
Yes.
Which one's colder? It felt cold too.
Yeah, they're in the right hands. Okay, so what claim can you make about the yellow substance and the pink substance based on your observations about their IMFs? Ready, set, go. Sorry, people at home, you don't get experience. Yeah, do both. Or just like compare them. Yeah. Once you have it down, I do want you to talk to your neighbor because I want you to hear different viewpoints. Sorry for those of you that got drips. Benny had the best idea, but he's like the last person I sprayed. So note to self next year. Once again, once you and your table buddy both have something written, share with each other what you wrote. Because even if you have the same claim, it's good for the brain to hear like different ways of explaining it. And then keep this claim, evidence, reasoning idea every time you do a justification. Right? Every time there's an FRQ. Silicon? Yeah, I'm pretty sure it's silicon. If you flip it around, it does have a label on it. Is it just S?
It's sulfur.
Oh, then it is sulfur. I knew it had an S on it, but I couldn't remember which one it was. Oh, yeah, the electrons are faster than trying to figure out like how many grams of stuff in there.
Liquid one.
Yeah, because as the vapor pressure increases,
Because like if it's held less tightly, it's easier.
You're on top of it, we'll just like steal it and something.
Maybe, right? I've seen a funny joke where a science teacher put a bunch of these on the ground and then one of those signs that said like caution water, like slippery. Jokes.
Does vapor pressure only work like with water, or could you do it with other substances?
No, everything has a vapor pressure.
Oh, okay.
Yep, it's just, I guess anything that naturally is a liquid has a vapor pressure.
Can we use the word? Can we use the word vapor pressure in this case?
You could, yeah, you definitely could. Vapor pressure could be connected as part of your reasoning. No, but it's real. You could still relate it, you know. So, okay, let's hear two different answers just to get some different views. Someone who hasn't got an extra smiley face today want to share. Annika, let's hear it.
I said the yellow substance had weaker IMFs because it evaporated very quickly, which means the boiling point is lower, and so the molecules are held together weakly.
Perfect, good. If you did a claim about how this one must have weaker forces, you're on the right track and can have a smiley face for that. So, Annika, you have two, one for your claim and one for sharing. So this is acetone. It actually says alcohol, but I put something else in it. It's acetone, which evaporates very, very rapidly.
I guess the yellow bottle must have been like a lot of pressure because we're holding it.
No. So that's the interesting thing is this one felt cold, right? They're the same temperature. But the reason why it feels cold is because of how quickly it's evaporating from your skin.
It's like taking
Yes. In the process of evaporation, it's sucking the heat from your body to evaporate. And because it does it so quickly, it feels cold. That's why you feel cold when you get out of a swimming pool or a shower, is because the water starts to evaporate off of you, pulling the heat out of your body. But this one does it so quickly that it feels cold like instantly.
So the bottom not under pressure because it's not trying to evaporate.
It definitely, I mean, it would definitely have a higher vapor pressure than this one for sure. Not to the point so much that like I have to like do something about it.
Yeah.
But like if I were to leave this lid off,
It would slowly drain.
it might not be here by next week. Like that's how quickly it just evaporates on its own. So, you know. Yeah, Izzy.
Can you make alcohol a hot liquid?
What do you mean
Like,
by
it
that?
has a low boiling point, so could you make it hot as
Oh.
a liquid?
Not as a pure substance. Yeah, or a pressure cooker. But it'd have to be like mixed with other things.
Cooking alcohol.
Like, hey mom, let me try this out here. Okay, one thing before we transition into our next demo and observations. Okay, this is here. Try, don't read that yet. Okay. What I want to point out is there are times where observations may not match your first instinct, right? We have talked about and repeat again that generally speaking, if something has dipole forces, it's going to be stronger than something that purely has London. But if you remember from last time, there was a chart, this one right here, where there's an overlap region. There's a point at which dispersion forces can be greater than a combination of a dipole and a dispersion. Now, you don't have to memorize those exceptions, but if it shows it to you in data, you need to match it to the data. So for example, this says, the boiling point of BR2 is 332 Kelvin. Now what type of forces does BR2 have? Just London. Okay? Whereas the boiling point of BRCl is 278. What type of forces does BRCl have? Yeah, this one has London and dipole. But what did the data claim or show? It has a higher boiling point, and so its IMFs must be stronger. Now, without the data, you're not expected to know that. Like Like if this was just a sorting question and it just had BR2 and BRCL, you would be expected to put BRCL ahead of BR2. But based on the data, we need to be able to explain this difference. And this, so this is from, I think it's last year's test. This was a question that was on it. And this is like the corresponding answer rubric of how it was graded. Okay? So it says, the only intermolecular attractions in BR2 are London, while those in BRCL include both London and dipole. Now notice that sentence is important because of how it talked about addressing each. Okay, pay close attention to bolded and underlined things in a problem to make sure you don't just miss that point, even if you're like, oh, I knew that both, but only addressing one. Okay? Then the second part says, however, due to the greater polarizability of the electron cloud of BR2 compared to that of BRCL, the London forces are stronger than the combined intermolecular forces of BRCL. And so that's how we justify the fact that the boiling point of BR2 is greater than that of BRCL. So, questions on when kind of exceptions to the general trend might come up?
What's these like the J or the L for next to the
Oh, so that's a way, we'll learn about it more in Unit 4, but like it just indicates it's a liquid. So we do little L's for liquid, G's are for gases. Is that what you're talking about, this little guy?
Yeah.
So yeah. They do a typically italicized L, I think, so it doesn't look like a number 1. So, okay, questions on that? Yes,
Do
Andrew.
you have to write the liquid, or could it just be understood?
Yeah, like it wouldn't be necessary to include that.
Okay.
Yeah. So we'll talk about when it is necessary. Like next unit we'll start writing out full reactions and then you do need to label them. But like in an answer like this, it wouldn't be necessary. So okay. I'm gonna skip this problem for now. We'll come back to it. But let's talk about chromatography to end today. Okay? So keep in mind, the theme is still IMFs. We're just talking about something that happens, but it's all still because of IMFs. So let me explain the basic setup of a chromatography, and then we'll understand the why. Now with chromatography, we're going to do a chromatography lab in this unit. It's not till it's not next week, but I think the next week is when we'll be doing it. So get a basic understanding today, but know we'll spend more time with it. So if it still feels a little bit like, I get it, but not all the way, it's okay for today. But the basic of chromatography, first off, does anyone remember, we actually said this word like, I think it was like one of our first or second lessons. Never remember what it was relating to? Remember, Brendan?
Like mass spectrometry.
Ooh, it was close to that, but it was different. But it's close to that day.
Isn't it like sorting stuff by color?
Yes, it was that day where I had like gravel water, salt water, and you had to like come up with your crazy way of how you could sort them. And I had a mixture of food coloring, and I asked you to sort out the red and the blue from each other, or figure out what colors were in it. Chromatography would work great for that. That's the prefix chrome is because typically it is done with different colors in a mixture. It doesn't technically have to be colors to our eyes though. I've done chromatographies under black light. So to our eyes it looked like the same color, but under black light you can see a separation. But here's the basic idea. So with chromatography you get a special type, it's not it, but just to give you an example, of paper that you're going to use. You then put a little dot of your sample near the bottom of it. Okay? So let's say I wanted to see what was in this ink, because black is a mixture of things, right? Okay? I then would stick this paper inside a beaker with a little bit of liquid. Not a lot. Because I don't want to submerge it, because then it will just dissolve. But I'm going to stick it in the liquid like this. And then what would happen if I stick this in some water?
It'll slowly.
Yeah, the water, because of IMS, will start traveling up the paper. Okay? As it travels, it can separate out the different things within it based on intermolecular forces. Okay? So, the key part here is there's not a one way all the time. It depends on what type of substances you use. Okay? If the paper is very not very solid, all paper solid. If the paper is a polar substance, then you typically would use a liquid that is more non-polar because you want the contrast. And then vice versa, if you had a more non-polar paper, then you would maybe pick a polar solvent.
If you have like non-polar paper and like non-polar liquid, you just like not trying to paper.
Yeah, that's the problem is then, as long as, you can do polar and polar as long as they're not, like if there's a difference, like one's really polar, but yeah, otherwise you don't get a good separation of it.
If it's polar and polar, then right?
So the idea here this is if I have, so let's say if my black dot, okay, well let's actually go with this, let's say the red. So the red within the mixture, let's say if this is extremely polar, what does that mean about the paper it's attached to?
It's non-polar.
What does it mean if a molecule is polar?
It's a positive.
Good, it has a positive side and a negative side. So if you have one thing that's polar and another thing that's polar, how do they feel about each other? They love each other, right? Polar and polar things love each other. What about a non-polar thing and a polar thing? Do they repel?
No.
They just don't love. But it's not a pushing away, right? It's just like they just hug themselves and they don't reach out to the other because there's no magnetic interaction, right? It'd be like the magnets are gone in this, and so there's just no force, right? So if something stays close to the paper, meaning it doesn't travel with the liquid, then that means its forces must be similar to the paper. And the ones that traveled the farthest, their forces must be more similar to the water, or whatever liquid you used. Izzy?
So does that mean since water is polar, the special paper that you use is just non-polar paper?
If you use water, but you don't have to use water. You could use an alcohol, or you could use hexane. Like you can use any liquid you want, depending on the separation you're going for. Nate? Oh, did I answer it? Okay, perfect.
How do you know the difference between polar and non-polar paper? Like, are they labeled non-polar
Yeah, you buy it.
paper?
Yeah, you can't look at it and know, but you just like, when you buy, depending on what chromatography you're doing, you would pick, like I'm gonna purchase this type of chromatography paper.
Okay.
So yeah.
Well, if you buy like two pieces of polar paper, will they stick to each other?
Yes, but not to the strength that we're gonna see. Because it's like, at that point it's not strong enough to like, at the molecular level, but yeah. Brendan?
Wait, so they make special like chromatography paper?
Yes. Yeah, so when we do our lab, so in our lab we're gonna actually separate out the colors in different candies. So like candies are used with food coloring, and there's lots of different types of food coloring. So like in a purple Skittle versus a purple Spree, you're gonna separate out that purple and see if they're made up of the same things. Or do they actually use a different combination of them? So yeah.
Could you just use normal paper for chromatography?
You could, yeah, you totally could. Once again, depending on what the substance is, it may not give you good results, but no, you can totally do it. Has anyone ever done, sometimes they do like Sharpie tie-dye. Has anyone ever done that before? Where you use Sharpie on a t-shirt, you draw, and then you spray it with alcohol?
Yeah. It's fun.
It's working through this process because the alcohol is causing the ink to spread throughout the t-shirt, so yeah. David?
What day is the lab?
I think, so not next week, which is Tuesday, Thursday. I think it's the following Monday.
So it's
November.
Halloween.
Oh, Halloween? Maybe.
Have fun in our costumes.
That I guess working with candy on Halloween, right? So maybe, it might be Halloween. I'll have to look and see. Okay, any other questions for now before we analyze a problem to sink it in? Okay, one last thing because we got 3 minutes left. I'll change it, but just in case, so we didn't get to 3:10 and that's okay. So we have a few more demos we're gonna do, and then you don't need to do the homework or the AP classroom quiz associated with 3.10 yet. Because we'll go over that stuff. So, okay, looking at this problem, label it with me here. This is the before, this is the after. Okay, so before you start chromatography, this is how it would look. This is how it looks after. Often when you do it, you compare knowns to unknowns, otherwise it's just dots on a page. So they analyze sample A, dye A, B, and C, and then they have this unknown, with the goal of seeing, oh, well, which of the unknowns is it? Okay? The other key thing when you read a chromatography problem is paying close attention to what type of paper and solvent they're using. So circle these words here. The paper is polar, and the solvent is nonpolar. Because your logic can be right, but if you don't read that, you could get it backwards. Okay? So the question here says, which dye, A, B, or C, is least polar? So based on how they separated, based on what we circled, which one is least polar? Show me an A, a B, or a C. A, B, or C. It would be C. So if you said B, you're just opposite. So since the paper is polar, B must be very polar because it's stuck more to the paper. C traveled the farthest, which matches the liquid. Solvent's the fancy word for the liquid you're using. So the nonpolar thing traveled with the nonpolar solvent. So that's kind of how you can, like, using a chromatograph, understand what properties they have.
So, but if you had like a non-polar paper, why would it do the same thing? Because polar, non-polar and polar also don't want to stick together.
So nonpolar and polar don't stick, right? So if you did the opposite, you would see the opposite result of where the polar things would get pulled farther.
But why wouldn't the non-polar things also?
They get pulled some, but it's that thing of where a polar thing doesn't hug a non-polar thing, right? They don't attach to it. And so since it's not going to attach to the water, it's going to get pulled less than something that the water's like, I'm going to take you with me because you're polar too. Does that make sense a little bit? Michael?
Then why does non-polar stick to the non-polar?
It's not so much that non-polar is sticking to the non-polar, it's more that it's just not sticking to the polar. Does that make sense?
So once get away from the polar, it's just being.
It's just like there's nothing to make it go with it. And so like it does move some, but compared to something that is truly polar too, it just doesn't get pulled as much. Does that make sense? Yeah, it's kind of, we'll talk more about this next time, but often people will say like water and oil repel each other. It's not repelling, it's just not mixing, right? Like water just hugs itself, oil just is there, but there's nothing that would force the water to interact with the oil, right? So, yeah, we'll talk more. That's what 3.10 is kind of all about. It's all about like solubility and mixing. Have a great lunch. You have a meeting after school. Do you have questions about your test? Yeah. Oh, like the correction papers? FRQ or module first.
What's that?
They're always on the module as well. If you ever like forget to grab one.
You guys still want those ones?
Sure.
Where's the multiple choice?
They're always just in the back of the letter that I missed, so yeah.
Is that
That's the FRQ one if you just want to grab one while you're here.
Okay, so I'm trying to get a question with my multiple choice questions.
Yeah.
And I cannot figure out how to find the multiple choice test. Because every time I try to go onto it, it says correct answers.
I didn't realize it was locked. I opened it during Skype time. You should be able to find it now.
And then can I get a multiple choice?
Correction sheet? Yeah, just go right back where Paxton is, and in the very, very back, you should see a tab that says like multiple choice corrections. It's just always back there.
And then do you have like FRQ tests?
Yes. Oh, this is over there.
We need Joshua Hudson to the counseling
Hopefully they
office.
realize that.
Joshua Hudson to the counseling office. Thank you.
Thank you. That's so silly. I got like a D on this, the other one, and I missed one on this one.
Oh, the multiple choice didn't go so well?
Yeah.
Oh, dang it.
But it's okay, that's like a B in general.
That's true, it averages out good.
Yeah.
That's interesting then. I wonder what it was
Yeah, me too.
that messed you up so much.